speaker is Chris Wysopal, and he will talk about data mining and a mountain of vulnerabilities. Thank you.
So it's good to be back at Hack in the Box. I'd like to thank Dylan and all at Hack in the Box for inviting me back. I was here 2 years ago, and it's great to be here. I had a great time. So today, I'm going to talk about the mountain of vulnerabilities that's out there. You know, if you look at CVE, which is publicly disclosed vulnerabilities, you know, we're in the order of thousands. But if you go behind the scenes and look at the vulnerabilities that are actually latent in the software because you've actually done inspection with automation or manual processes, you get to see a lot more than what really gets publicly disclosed. And there's a lot more data there to mine and figure out what's going on and why and how are all these vulnerabilities getting into our software. So first off, I'm going to look at some of the breaches from 2011. You know, 2011, a lot of people call it the year of the breach. It seemed like there was a lot more bigger breaches. I think Dark Reading came up with this list of what they considered the 10 most impactful breaches. They weren't like by dollar amount or records. It was just, you know, what seemed to be the impactful ones that really impacted people the most. And I went through the list and wanted to see what's the root cause. Because a lot of times we don't find out what the root cause of the vulnerability is. We just hear there was a breach, things were exposed, and the company doesn't really talk about it. And there are some of those here. If you look at Epsilon, WordPress, SciWorld, Steam, I'm still trying to figure out what happened, right? I send emails to people who might know, and if they're not going to disclose it, we just won't know what happened. And I think that's a shame because I think we can learn a lot from the mistakes that people make so we can learn not to make them again. You know, we do it with other places in society. When a building falls down or a plane crashes, we inspect it. We figure out what went wrong. Was someone negligent? Were things defective? Do we have to change our building processes? Do we have to change procedures? We don't really have a good model for that. So this is sort of my start at doing this, is just looking at the data out there, where they're coming from, what are causing the vulnerabilities. And so I looked at the 6 vulnerabilities that, the 6 breaches that we had data for, and 4 of them were application related. You probably remember Komodo, where a hacker ostensibly from Iran broke into the certificate authority right through their web interface. The interface they set up to do business with their certificate partners just went right through and found vulnerabilities in the web interface and made his own certificates and stole certificates that he shouldn't have had access to. If you look at RSA, that was obviously a spearfishing attack. We see that with APT. But we have to remember that the reason that that worked was it wasn't APT, it wasn't spearfishing where someone did something like downloaded, installed some software. All they did was view a Excel spreadsheet with a Flash object in it, and there was a vulnerability in the Flash player. So sophisticated, you know, APT campaigns are going to use vulnerabilities and getting people to consume data to exercise those vulnerabilities in the apps. If you look at Sony PlayStation, it's still a little vague, but some of the stuff that Sony said led people to believe it was something running on their application server. And Citibank was a authorization error. Essentially, they used an ID embedded in the URL to decide which customer's record to display, and they didn't check to see if you were authorized to display that record. So it was really easy to just change the URL. I mean, this is like a 1998 style attack. I can remember when I first got into looking at web vulnerabilities, that was one of the ones I tried all the time. So, you know, what's going on? You know, there's still these really simple things causing major breaches. So the question of the day is, who would release a product riddled with security problems simply to make money? and I didn't answer this, but the answer was pretty much every vendor out there. And that was an analyst, Andrew Hay, who covers the security space. And I think his point is, it's not every single vendor. There are vendors. Some of the major vendors work really hard at security. But I know that there's a lot of software vendors out there that do absolutely nothing. A lot of the smaller vendors out there, a lot of the websites out there do absolutely nothing. And they just don't seem to care. So building a secure application is not easy. Even educated developers make mistakes. I don't know how many of you knew I was involved with the Loft back in the 90s, but Mudge, Peter Zatko, had a rule. He said, if anyone codes a vulnerability, we're gonna cut off a finger. And in the release products that we did at the Loft, my hand would look like this. Okay? So I had 2 vulnerabilities in code that I wrote that got found by someone, were disclosed to us, and I fixed them. But I thought I knew what I was doing, right? One vulnerability was a buffer overflow in Netcat for Windows. The other vulnerability was I forgot to set the file permissions on sensitive data. I saved it to disk world readable. And that was in Loftcrack. So people make mistakes, even people that are educated and people who have peers reviewing their code. Things get through. But I think it's getting easier to write secure code because we have a lot of automation now that we didn't have when I was writing code at the Loft. We have static analysis. We have dynamic analysis or web scanning. And a lot of people still aren't using these techniques that are out there. And just from what I see with the different classes of vulnerabilities that we find for our customers and the amount we find, I think about 2/3 of the vulnerabilities out there could be found with automated techniques if people just use them. And the data I'm going to show today comes from over 10,000 applications that were scanned using automated techniques. And my last point is, since this is available, it's really a dereliction of duty for a development team to ship code that they didn't do security testing on. It just has to be thought of as not acceptable. And that's what when I talk to development teams, when I talk to customers, people buying code, people having people code written for them, that's the point I try to get across. So one new trend that we're starting to see increase is water holing. And RSA discovered a campaign called the VOHO campaign that happened over the summer. And they looked at how are these people getting in? How are they getting past the perimeter? And they looked and they thought, well, it must be spearfishing, right? People are sending spearfishing emails, tricking people to open attachments with malicious payloads or click on a link that goes to some website that's hosting a malicious payload. And they found out that this campaign was different. The attackers, what they did was they broke into websites that they thought that the individuals at the organizations they wanted to compromise would visit. So they kind of profiled the people there and found sites that were of their interests. One was, I think it was a rugby organization or something in Canada. So they knew people at that organization played rugby that they wanted to attack. And they broke into those sites, which are usually small, insecure, community-oriented or small business sites, small government organization sites, and they compromised them, and they hosted the malicious content there. And they figured eventually someone at that organization would go to that site. So they didn't even have to do a spearfishing attack. So we're starting to see that the security of just every web application that's sitting there on the internet really impacts all of us. It isn't just the major sites. It's the mom and pop sites out there could be hosting malicious content, and someone could have put that content up there specifically targeting your organization. And we're starting to see that happen more and more, and I think it's going to rise to the level that spearfishing does, because people are aware of spearfishing. Their eyes are open that they shouldn't be clicking on links that seem a little bit strange. But I don't think they're doing that when they're going just to visit a site on the web that they're used to visiting. So, the attackers, you close one hole of getting that malicious payload onto that user's machine, and they're going to find another one. So now I want to get into the data. So this is the data set we have. It's applications we scanned from over 300 organizations, some US government, mostly large enterprises in the United States and Europe, some small software vendors. And it's just under 10,000. It's 9,910 applications we scanned over the last 18 months. And they vary in size hugely. We have small, little tiny apps of 100K to 6 gigabytes was the largest one. So applications come in all shapes and sizes. And when we scanned this, these were code that, some of this code was production code. They had shipped this to customers. Some of it was pre-production, where they were using security testing as you should during the development cycle. And it comes from lots of different sources. Internally built code, the kind of code that an e-commerce company might build, a finance firm might build, or commercial code that people are building to sell, software vendors, to outsourced and open sourced. It was whatever our enterprise customers were concerned about finding vulnerabilities in. And so we just don't have the vulnerability data. That's the scan data, we call it, where line of code, the kind of vulnerability, but we have metadata about the application. What vertical? Was it finance? Was it software? Was it transportation? Was it media? We know how the software got produced. Was it something that was internally built or something they purchased? Assurance level, how critical did they think this piece of software was? And of course, the language and platform it runs on. So we have that metadata about all the applications. So when we find a vulnerability in the application, we can use that to look at some trends and slice the data and start to make comparisons. And then we have a lot of different application security metrics, which is what we report on outside of just the vulnerabilities. So counts, percentages, time it takes to fix things, holding the application up against external standards like OWASP Top 10 or CNCWB 25. So the data set here, you can see that most of it's internally developed code. 72% is built by the companies that are sending it to us. About 18% is code that's written by software vendors. And 9% is open sourced, and 1% is outsourced. It's interesting that we don't see a lot of code from outsourcers being security tested. My theory there is the outsourced contracts are very strong. They're like 10-year contracts. And so when the enterprise, say the bank, says, hey, I want to test this and have you fix the problems in the software, the outsourcer says, no, you can't do that. Or they say, oh, you can do it, but you're going to have to pay to get the vulnerabilities fixed. We put them in there for free, but you're going to have to pay to get them fixed. So when you have sort of those dynamics, people don't even want to know because they don't have the budget to fix them. And then down here is a breakdown by language family. So you can see the different languages that we're scanning. Java, by far, is the most prevalent language out there that enterprises use the software they're running. Followed by .NET, C, C++, PHP, Cold Fusion, Android, iOS, and J2ME, tiny little slivers. And it's not, we do have hundreds of mobile apps that we've scanned, and I have data on those. It's just that compared to Java and .NET, it's just totally dwarfed. So I want to explain the difference of the latent vulnerabilities versus vulnerabilities that are attacked. Right? The latent vulnerabilities is, yeah, it's there sitting in the code. But if no one attacks it, who cares, right? But it's useful to understand because if attackers change start attacking a different kind of vulnerability, then all of a sudden all those latent vulnerabilities of that category become more dangerous. So I made some comparisons here. In the blue is the data we get from the web hacking incident database. And the reddish here is the data that we got at Veracode from mining our data. And so take SQL injection, for instance. 32% of the web applications that we tested had at least one SQL injection vulnerability in it. Could have had dozens or even 100. Typically, we don't see that many. But we definitely see several. It's rare that's just one. But at least one put it in this category of 32%. And then if you look at the percentage of hacks out there of websites, 20% of those hacks are using SQL injection. So you can kind of see that, yeah, that 32% latent vulnerabilities is really, really meaningful, right? Because 20% of the attacks are actually attacking that vulnerability. So when you look at the data this way, you say, I should at least be getting rid of SQL injection because there's a lot out there. 1/3 of the apps have it. And in my organization, 1/3 of my apps probably have it unless I'm doing something about it. And from this data, we see that 20% of the attacks are leveraging that vulnerability. So I like to use this to show developers that, yeah, the vulnerabilities in the code really do get attacked. Cross-site scripting is interesting because cross-site scripting we see in 68% of the applications. We see that all over the place. But it's only implicated in 10% of the data breaches. And my explanation, I think, for that is it's really harder to get at the attackers, what the goal of the attacker is a lot of times with cross-site scripting. Only certain kinds of sites with certain goals of the attacker is cross-site scripting going to be as interesting as something like SQL injection. And then it goes down from there. We see information leakage is all over the place. That's very common. That's when you're giving up data that the end user shouldn't see, like internal IP addresses and paths and version information. That's pretty common. That was implicated in 3% of the attacks. It's probably implicated in more. It's probably more of a reporting issue. I know when I'm pen testing, I love those information leakage vulnerabilities to help me find other things. And then this one's interesting. Cryptographic issues, we find 53% of the time, but it's only implicated 2% of the time. And I think that's just it's really kind of hard to exploit those. A lot of times, a cryptographic issue is you're using a weak cipher or you have a hard-coded key in the application. And those things are pretty hard for an attacker typically to go after. And the last one is interesting because it's only in 9%, but it's used 1% of the time. So that ratio is very different than 53 to 2, 9 to 1, which I think tells us something. So command injection is a little bit more rare. I mean, obviously, it's more rare than the other ones. But since it's used 1% of the time, attackers must be looking for it. And it must be something that's interesting to them. Because it seems the ratio of latent vulnerabilities to ones that are attacked is it's higher than crypto and info leak. And that's because command injection is a wonderful vulnerability to find, right? You can execute commands on the server with the permissions, privilege level of the application. That's very useful to attackers. So now I'm going to dive in a little deeper here into these vulnerability categories. So this is the top vulnerability categories, percent of applications affected for web applications. So this meant the application had one or more of that kind of vulnerability. So some of the data was on the last slide, but you can see cross-site scripting, command leakage, information leakage, control line feed injection, carriage return line feed injection, cryptographic issues. In more than half of applications were finding those vulnerabilities. Directory traversal, which is another one that attackers, I would think they would like more. It didn't show up in that top 5, found in half the applications. And there we are with the SQL injection. Interestingly, I've colored the bars orange if it's in the OWASP top 10 and blue if it's not. And you can see that the OWASP top 10, which is, it's kind of anecdotal, right? It's a bunch of web application experts getting together saying, you know, what do you see a lot of? What are attackers attacking a lot of? What are the most impactful vulnerabilities? And it actually turns out that they mirror the real world data that we're finding. We're finding the data out there that matches up with the OWASP top 10. So I think these lists are actually pretty good. If you could eliminate the OWASP top 10 in your application, you're going to be doing very good. Now, this is another statistic. This is prevalence, overall prevalence. So this took into account the count of the vulnerabilities. So this can give you an idea of just how much cross-site scripting is out there. 57% of all the vulnerabilities we find in web applications are cross-site scripting. So, and so a lot of times if you don't just have one cross-site scripting, you have 100 cross-site scriptings in your application or even more. And that, one of the problems with that is it can be overwhelming to developers to fix it. But cross-site scripting is a major problem, and I don't see it going away anytime soon. Followed by carriage return line feed injection, information leakage. SQL injection is only 4% of the vulnerabilities out there. It's a very bad vulnerability, but it's fourth most common. And then you can see down the line that we get into 1% and less than 1% pretty quickly. So if you're looking at the vulnerabilities that developers are going to have to fix, a lot of them are just in the top 5 category. If you trained your developers just to fix those and know about those, you'd be eliminating a lot of vulnerabilities. Now let's look at some non-web applications. So non-web applications, we have different kinds of vulnerabilities show up. A lot of these applications are written in C and C++, which have a whole range of issues because the language is not type safe. So you have issues with overflowing integers. You have issues with overflowing buffers because at the language level, the language isn't tracking overflow or underflow conditions. It's just letting you do whatever you want. And so you can see that we don't have cross-site scripting and SQL injection. Actually, we do have SQL injection. It's way down on the list. Because, of course, a non-web application can use a SQL database and connect to one. But we don't have cross-site scripting. And so we have a different prevalence. So cryptographic issues, this kind of surprised me that this was this high. And I think this shows us that developers just don't know how to implement crypto. You know, they see the API, but they get it wrong. They pick the wrong ciphers. They pick the wrong flags. They don't check certificates. They embed keys in their applications and think that that's fine. So if attackers were to start learning more about crypto, I think we'd be in a world of hurt. But as we saw from the earlier slide, they just don't seem to be going after that stuff. Directory traversal, very common. Error handling, information leakage, potential backdoors. And then we get into sort of the unique things for non-web applications like buffer management errors. We see command injection is a lot higher. We see numeric errors, a new category. So we got a lot of new categories here for non-web applications. So this is the percentage that was affected by these. So for instance, 14% of the non-web applications have buffer overflows in them, which is a very, very problematic vulnerability. Oh, I should have mentioned back here that I colored in green what was in the CNCWE top 25, which again is kind of like the OS top 10. People get together that do a lot of application level work and pick out the categories that they think are the top 25 most important categories. And it lined up pretty well with our data. There was a few in there like error handling, potential backdoor, time and state that showed up that aren't on that list. But in general, it was pretty good. Now this is overall prevalence. So this is sort of just as the absolute count, the number of vulnerabilities that are out there. It's no surprise that, that error handling is often gotten wrong. People just forget to check the return code when they open a file or something like that. But you can see that these really serious vulnerabilities, buffer management errors, which can lead to all kinds of arbitrary executable code, buffer overflows, numeric errors. These are all really serious vulnerabilities, and they're extremely prevalent out there in the non-web world. So now I want to break it down by language, because language matters. I mentioned in the non-web, the reason that a lot of those vulnerabilities were at the top was because a lot of non-web apps are built with C and C++, which has those vulnerabilities. So now I just want to look across the different vulnerability category, different languages. And if you look here, starting with Java, cross-site scripting is number one. Not a surprise. It's the number one category overall for web applications. Java, we write a lot of web applications. Then we got control line feed injection, information leakage. So since Java is so prevalent, it's kind of mirroring what we see overall for web applications. But then we take a look at Cold Fusion, which really isn't used isn't as prevalent, and it has an even worse cross-site scripting score, right? 87% of the vulnerabilities found in Cold Fusion are cross-site scripting. So you look at that and you say, well, something is wrong with cross-site scripting. It's at the language level, it's easier to have a cross-site scripting vulnerability. And that was totally true up until, I think, about a year ago. And Adobe actually put a fix in for Cold Fusion that at the language level did some output encoding to help prevent against cross-site scripting. So I don't have sort of the before and after, but I can tell you that it dropped a lot. And that shows what happens at the language level makes a big difference, or at the platform level makes a big difference, because the developers aren't paying attention at all. So if you have a language or a platform and you want that to be more secure, don't train developers to write correctly. You can do that, but it's going to make a much bigger difference to actually write code at the language level that will prevent the vulnerability from ever occurring. And then if we look at C++, we have error handling, buffer overflows, buffer management errors. So these are the problems that C and C++ developers have to deal with. You look at .NET, and I like to compare .NET and Java because they're kind of written in a lot of the same context. So we have 47% cross-site scripting versus 56. Second category is information leakage versus control line feed injection, so 10% versus 18. But then on .NET, we have 10% cryptographic issues where we didn't have that on Java, and in the top three anyway. So that tells me something about the way that the .NET APIs are built, or the way developers are educated about how to use them is better on Java than it is on .NET. That's just me trying to explain the data. I don't know if that's absolutely true, but there's got to be some explanation. Or maybe .NET developers are just not educated in crypto as much. Now if we look at PHP, you'll see why PHP has so many websites that are PHP, built with PHP get broken into. Because we have our friend here, cross-site scripting, not a big surprise, but we got SQL injection is making it into the top three here, and directory traversal, another great vulnerability for attackers to leverage, is making it into number 2. So you can see PHP at the language level, or how developers are trained to use it, they're creating a lot more directory traversal and SQL injection errors. If those same applications were written in Java or .NET, it's likely they would be more secure. So the language definitely matters, especially in web apps. And then here we have Android. Just to see, Android is a completely different, right? We're talking about a mobile platform. It's using Java. But the vulnerabilities are different than Java. We're getting a lot of crypto issues. We're getting 44 versus didn't make it in the top 3. Control line feed injection was about the same, maybe higher. And then information leakage. But number 1 is crypto issues. And I can tell you what that is. The number one issue we find is, well, there's actually two, is developers on Android versus their counterparts on making, say, enterprise Java applications. You're writing in the same language, but the errors are different, which is interesting, right? So it's what kind of apps are people writing? And crypto errors turn up very high. And we see that developers are embedding keys into their application, and they're also implementing SSL incorrectly. They're doing things like turning off certificate validation. And so, you know, I think education can probably help there. So now if we look at by the supplier of the application, so someone built the application that the ultimate end user is running. And if the supplier is internally developed, that's the enterprise built it for themselves. That's the e-commerce site building their own app, or the financial firm building their own applications. Then we have commercial, which is the customer is purchasing the application they're running. Open source, that's self-explanatory, right? They're just downloading an open source application, and then outsourced. They're paying someone else to build a custom app for them. And I thought it was interesting to look across these different supplier types to see if there are different kinds of vulnerabilities coming from different supplier types. So is there going to be a difference whether you're buying an app or using open source? And if you look at cross-site scripting, it's kind of interesting. It's kind of number one everywhere again. But for outsource, it's a little bit lower. Really don't have an explanation for that. One of the problems with the outsource is the sample size is really small. We only had about 1%, so it's only about 100 applications. But then if you look at something like SQL injection, we see that it's about the same, 4%, 3%, 3%, but there's a lot more vulnerabilities above SQL injection in commercial code, and there's a little bit more in the open source code. And if you look at directory traversal, this one was the most interesting one because it seemed like the most varied across, where it was only 3% in internally developed, goes to 6% in commercial, and then open source has 13% directory traversal. So I don't really have a good explanation for that, but I mean, these are sample sizes of hundreds and hundreds and even thousands of applications. And we're seeing a very distinct difference between internally developed code and, say, open source code for some categories. Buffer overflows only shows up in commercial code. That's probably because most internally developed code is not written in C and C++. But I thought it was interesting that it didn't show up in the open source code. You know, there's a lot of C and C++ open source applications out there. Why is it showing up? You know, add these together, 7% of the vulnerabilities are buffer management, buffer overflow type issues in commercial code, and it's less than 1% because it doesn't even show up here in open source code. So that was another very distinct difference. I don't know if the open source guys they understand how to manage their buffers better. I'm not sure why that's happening, but that was another distinct difference. So then I decided to look across industry. So this is the industry that's running the software. So it could have came from anywhere. They could have built it themselves. It could be open source. It could be commercial. And they're running the code. And you can see that if we look at the government, and this is mostly US government, we have 40% of their applications, or 40% of their vulnerabilities are SQL injection, versus 29 for finance and 30 for software. So if you're going to break into a government app, I guess use SQL injection. But you know, it tells me something, that they're willing to accept more risk of this vulnerability that is obviously used very, very often by attackers. It was 20% of the web attacks, most common web attack. And government's accepting more risks. So this tells me government's application security testing is more broken than anyone else's. I think that was the only pattern I saw that they could make any significant differences But this stuff will all be in the PDFs distributed, and you can dive into the data a little more yourself. So let's talk a little bit more about developers, because we're going to pile on to developers, right? So I looked at the data and wanted to see if there was any trends, because we have data that this data goes back 18 months. And actually 2 years, almost 2 years here. And wanted to see if there's any trends. Is all the hype about web applications getting broken into sinking into different organizations? And so we looked at cross-site scripting and the percentage of apps that were affected, and it actually turns out to be flat, right? It looks like it's going up a little bit, but we computed the p-value, which shows if it's statistically significant or not. And there wasn't a significant trend here. So pretty much we're holding steady with cross-site scripting, right? We're using the same languages, we're testing apps the same way, developers are trained just about the same, and cross-site scripting is staying the same. We can expect probably 67% or something of apps to have cross-site scripting next year, and perhaps the year after. But one thing that was really interesting was the word is out, it seems, on SQL injection. We did the p-value, and statistically, this trend is significant. And it starts here at about 39%, and it goes over to here at 32%. So it's gone down 7% over about 2 years, which is significant. And this gives me hope, right? It gives me hope that all the talk about SQL injection and demonstrating to developers how easy it is to do breaches is sinking in. And development organizations are saying, we should be at least testing for SQL injection, at least fixing this. The problem is, at this rate, it's going to take like 15 years to get lower than like 20%, because it's so slow, right? So tiny bit of progress. Some people are getting the message. And then I did a little bit deeper dive on the trends for the US government. This is for cross-site scripting. It looks like it's going up. The gray line there is the overall trend, and the orange is the government trend. But statistically, it's still flat. So the government is doing worse than average, but they're staying steady at worse than average. They're not getting any worse. Whatever consolation that is. Okay, so now looking at a pass-fail policy. So we allow our customers to pick a policy and say, I want my app to have no OWASP Top 10 vulnerabilities in it. And we can do automated testing, we can do manual testing. But within whatever kind of testing we do, the categories we test for, they can put a policy in place that says, if there's one issue in the OWASP Top 10, that app is going to fail. The development team is going to have to fix it. And so this is a common policy that we see with our customers. So whether this is commercial code, outsourced, open sourced, this is all the apps we see. Let me just see from a show of hands here, what percentage do people think is A? 34% fail OWASP Top 10. Okay, nobody. How many people think it's B? 57%. Nobody. How many people think it's C? 86%. Okay, we got a few hands, about 10 hands. And how many people think it's 99%? Okay, we got more, a little bit more there. So that's a kind of pessimistic crew, but I think I've set you up for that. So actually, the answer is C. It's not quite 99%. It's 86%. So this is the overall 86% fail. And then you can see that open source actually does the worst at 94%. Now remember, this is just web applications. Commercial has 86, right on the average, and internally developed, right on the average. So it's kind of interesting that if you slice it by OWASP Top 10, the code's almost the same depending on where it came from, except for open source, which does worse. So, think about all those web applications you're downloading for open source when you see this test results. So I won't quiz you again on this one. This is if you do the CNCWE top 25 on non-web applications. You use that as a policy, and you say if there's any vulnerabilities in there, in that list. And you can see, again, open source does the worst, followed by commercial, and internally developed actually does the best. So I thought that was quite interesting. So one of the things that people can do when they're building the code themselves is hold their internal development teams accountable, right? The CISO can put a policy in place and says, we're not putting that online banking app up until we've done adequate security testing and remediated all whatever we deem to be the policy that's not acceptable, let's say the OWASP top 10. And of course, for banking applications, that happens. But there's a lot of companies that have web apps with sensitive data out there, customer data, other sensitive information that aren't doing anything. So that's sort of the landscape for internally developed apps. But when it's a commercial application that the customer is buying, right? So they're buying a piece of software to run their business, they can hold their vendor accountable. They can say, you know what, as part of this acquisition process, I want third-party testing. Just like you might audit a service provider's, you might do a infrastructure pen test. A service provider that maybe you're sending, you're doing online backup to or something. Companies will send a team out there and do an audit of that. Well, you can do the same thing on the software you're purchasing and just say, I'm not going to, just like I won't accept my own developers putting flaws in that are in the OWASP top 10, I'm not going to accept it from the developers I'm purchasing it from the vendors I'm purchasing from. So we do this kind of testing too. And this is the data from the different industries that are having Veracode test the software that they're purchasing. So the biggest always seems to be other in all these kind of charts, so the other industry. But the number one is finance. So 21% of our customers doing this are finance customers, followed by the software industry. Isn't that interesting? The software industry is testing the software that they're purchasing. Do you think they know something? And I think a lot of it is not just to run their business. A lot of the code that software companies purchase, they bundle with their software. So if you look at a large software package, there are components in that software package that a software vendor licenses from other software vendors. And that's where we're actually seeing this happen a lot. So these are kind of enlightened software vendors that are testing their own code, and they're testing the code from other vendors that they're purchasing. So I thought that was pretty interesting. Followed by the tech industry, telecom industry, health, business services, and then media. Government's not doing so much, only 3%. This is aeronautical and defense industry, EDU, and utilities. Isn't it funny that EDU and utilities are doing this about the same? Utility is way behind the curve on this stuff, right? They should be up here with finance, right? And then these are the purposes of the application. So this is what it did inside the company. So number one category is operations software. So that's IT operations, other things that the companies use to run their business. Followed by other. Followed by security applications. So 3.8% of the software we're testing is security software. So people are buying security software, they're testing the security software, and I have some really interesting numbers on this I'm going to show you. And then followed by web applications. I guess that's web infrastructure. Followed by customer relationship software, followed by financial software. So I guess I should have done this in percentage order. But you can get the idea of the types of applications companies are concerned about. And then here's the pass-fail, right? So the companies set the policy. They could set OWASP top 10. They could set CWE 25. They could say, we just don't want any high criticality vulnerabilities. And this is how the different industries turned out. If you look at the top here, the industry sector that did the worst are security products. Only 26% of security products passed whatever the purchaser's policy was. Contrast that to financial, which had 58% passing. So security software is much more vulnerable than financial software. Think about that for a minute. And then the next category was operations. So this is other software that's running IT infrastructures. This is like ticketing systems and log management software and software that's dealing a lot of times at an administrative level on the system. Second worst code. Healthcare also did very poorly. It's interesting that learning and growth did the best. I think it's really because the policy on learning and growth wasn't very strict because there's not a lot of critical data there. And the policy may have been more strict on things like operations and security. But that's okay, right? The policy should be more strict. At the end of the day, it didn't meet the policy. It had vulnerabilities that shouldn't have been there. So then we looked at all the different software vendors, and we broke it down as public versus non-public, and then we broke the companies down by revenue. So I had an interesting blog back and forth with Marianne Davidson, the CSO of Oracle. And she wrote this long thing that basically said, you know, what Veracode is doing, it's okay for small vendors. Because small vendors, yeah, they write crappy code, and they don't know much about security. But Veracode's really bad for big vendors. Big vendors don't need to be held accountable. You should just trust big vendors because we all have application security programs, right? We do a good job, and we got this under control. So these charts are because Marianne basically said, you know, she made a statement, and I wanted to say, well, let's look at the data. Like, where are you backing this up from, Marianne, right? So look at public versus private companies. Pretty much the same. These are whisker charts, so this is the median, and this is two standard deviations wide. Looks pretty much the same to me. So being a private company, which is typically smaller than public companies are typically bigger, we sliced the data that way. We saw absolutely no difference in our data set. And then we looked by the revenue of the organization from your smaller software company, less than 50 million, all the way up to your mega software companies with revenues over $1 billion. And look at this. It's almost exactly the same. The standard deviation is almost exactly the same. And so size doesn't matter when it comes to writing vulnerabilities. So now I have some data on mobiles. This is the trend, right? All the applications that used to be client server and desktop over 2000 to 2010, you can do almost all of those things on the web now, right? People built web applications to supplant all that desktop stuff. And now we're seeing another trend happen. This is going to happen over the next decade, is all that stuff that we used to interact with a web UI, we're just going to be interacting with a mobile application. Which is interesting, right? It really kind of changes the paradigm. It changes the risk model, the threat model. It changes the kind of vulnerabilities. We got new operating systems. So we wanted to take a dive here. And this is just the early days, right? We've only been doing this about a year at Veracode. We'll be doing web apps for 6 years. And the industry as a whole has been doing web apps for 14, 15 years even. And mobile only just for 2-3 years. So still the early days, but there's some interesting trends we saw. So I don't want to go through all this like I did before, because I'll bore you to death, but these are the industries that we looked at. And you can see, I'll just point out media was #1, because media companies, they're using this as a distribution mechanism. They're writing a lot of mobile apps. And then I think #2 was other. And then financial services, writing a lot of mobile apps to run their business. And then if you look at how are these apps being written, this is very different than our other data set, right? When I had in the beginning was I think over 70% were internally developed, and then the other ones were vendor code, like at 15%, and then we had like 10% open source, and then we had a little bit of outsource. This is very different. Internally, we have a lot more commercial applications here. Mobile apps, there's more of the mobile ecosystem is commercial versus developed internally. And then open source is pretty much non-existent. There's not many open source mobile apps, so that makes sense. I don't even think there are any on the iOS platform at all. So then I looked at the Android data, and #1 category is cryptographic issues, as I mentioned before. The Android developers just don't seem to understand how to implement crypto in their apps. And this is something that you need, right? Because you're transmitting this over potentially insecure network, right? If you lose your device, you want the stuff to be stored securely. So crypto is potentially even more important here than in the web world. Control line feed injection comes up a lot. That's not very interesting, right? You can muck up some data in the app, log files, but typically hard to exploit. Information leakage. Now, information leakage on the mobile device sort of has some new meaning, right? Because there's a lot more private information sources than if you think about in a server application. On a mobile application, you have, address books, contact information. You have location information. There's a lot more information that can be leaked on the mobile device. And then we even have SQL injection here, because a lot of Androids are using a SQL database as the back end, and some cross-site scripting even. Then looking at iOS, we see the makeup is pretty much very different, right? Error handling is now #1. I think this is because it's harder to do error handling in Objective-C than it is in Java. It makes it up to #1. We're still seeing a lot of crypto issues, still seeing a lot of information leakage, but now we're getting buffer management errors, code quality. You can see here numeric errors, buffer overflow. That's because they're written in Objective-C. So we're getting a lot more of those non-type safe languages. The saving grace here is on the iOS is all code is signed, right? It has to be signed on a non-jailbroken device, which makes it very difficult to exploit those vulnerabilities. So they could definitely lead to quality issues and potentially lead to security issues, but it's just much harder to exploit than in a lot of other environments because of the really strict code signing. So it looks worse, but it's actually better than Android. OK, so now I'm going to finish up with developers again. So we have an online e-learning platform, and we've tested over 10,000 developers. That's where this data comes from. So the question is, when given an exam on application security fundamentals, which is just it's an hour course with an assessment test, over half of developers receive an A. How many people think over half the developers get an A? OK, you're learning. How many people think they over half get a B or worse? We got 1. How many people think over half get a C or worse? OK, we got about 10 or 12. And how many people think over half get a D or F? OK, we got even more there. It's a pessimistic crew. It turns out that the answer is C. So it's not quite as bad. So if you look here, we have over half the developers getting a C, D, or F. So the average development team has 19% of the developers that fail, given everything. So do you want those people writing your code? So it just shows you that developers may think they understand application security, but in reality, really about a little less than half do, and half don't. And all it takes is a few developers on a development team to write a lot of security flaws that'll end up being exploitable. So that was all I had for slides, and I think we have some time here for questions. Does anyone have a question? Oh, over there. Okay, so the question was, when I was presenting data about by language, some I was talking about it's the language's fault, it's the developer's fault. And ultimately, it's the developer's fault, ultimately, because if a language is, say, missing, type checking, right? So it's allowing you to index past the end of your buffer, or it's allowing you to copy a big buffer into a smaller buffer. The developer has to be educated on those limitations and know that the platform isn't protecting from those things from happening. So ultimately, it's the developer's fault. My point was it's possible for the language and platform developers to build in some more security mechanisms at the language level so the developers don't have to work as hard. Back there?
Right. I'd like to make a statement of contribution rather than a question, and I hope that I'm correct, and if I'm wrong, please.
Sure.
I've been in application security for some time, and I find that a lot of the problems are more due to operational issues. For example, your last slide, I would claim that half the developers,
this one?
Yes, can get an A in application security. They know, but actually doing it, a lot of them will get an F. So a lot of it has this, I'll get back to you. They never get back to you and get a blue screen. Or we don't have budget for education and training. Or it's nobody's problem. Network security doesn't care about application. Application don't know what security is. And I see that, correct me if I'm wrong, everyone has the best. No developer goes to work intending to write bad code. But a lot of operational issues make things don't happen. You have 12 months to write some software with 3 months for QA, but 11.5 months later, you're still writing the software. So the hell goes to QA, or QA goes to hell. That kind of a situation.
Sure. So I agree. There's a lot of development organizations that aren't doing testing just because they're not budgeting for it, and they're not putting time in the development cycle. And I absolutely agree. It's just I don't have any data to show what those contributions of those problems are to the AppSec problem, because I don't have that data. All I have is looking at the artifact itself, or in this case, looking at test results. But I totally agree that's a big contribution. Anyone else over here?
Take into account the bias for issues like cross-site scripting and SQL injection, that they are resolved by frameworks, because a lot of modern frameworks and libraries take care of these issues, and the flaw may be in the code itself, but it has absolutely no effect.
So yes, there is a bias to our testing, right? If we don't look for an issue, we don't find it. The majority of this data is from automated testing. It is static and dynamic testing. We do have manual test results in there, but I think it's probably less than 1%. I should have the pie chart. I don't have the data on the top of my head, but I would say probably a little over half is static, and then lesser is dynamic, and then manual is a small slice. So you may have noticed there wasn't a lot of issues there that could be found only with the manual techniques, business logic, authorization issues, or a lot of the authorization issues. So I think if we had a lot of manual data, you would see some other vulnerability categories maybe rise up. But I still don't think that those would come anywhere close to some of the other issues, just because they're so prevalent both in applications affected and in the quantities of them. So there is a bias, but I don't think it's overwhelming that it would, all of a sudden we'd see authorization as number 5 on the chart. I don't think that would happen.
Right, if I use automated tool like hundreds of SQL injection, but if I actually do a pen test on it, it's a false positive.
So there's a potential if there was something in the environment outside of the application that was blocking these issues that we wouldn't see it if it was outside of what we inspected. And you're right that when you do a manual penetration test, you have environmental and network controls that can block and make things certainly non-exploitable. That's definitely true. So agreed. Do you have a question or comment?
So we know developers are not universally productive. Different developers produce different qualities of code despite productivity standpoint. Is there, do you think, with respect to vulnerabilities, do you think there's a Pareto principle going on that 20% of the developers are producing 80% of the vulns? We just don't know their names yet?
So the question was, are 20% of the developers producing 80% of the vulns because they're really productive writing buggy code? It's likely, and I would love to be able to do that. I would love to be able to correlate, the developer who wrote the code with the vulnerabilities, and then also look at what education that they'd had, and try to mine the data that way. But I just don't have that data. I know, like hooking into the source code control system can help with a lot of new code that's just being written. Okay, well, thank you very much for coming.
Thank you. Thank you, Chris.